Okay. Hello. So I'm finishing up my PhD at UBC just across the strait, and this is work that I've done with the CFEPS collaboration. So why should you, exoplanet and disk people, bother with the Kuiper belt? I'm another interloper, sorry. So the Kuiper belt is a planetesimal belt that has been sculpted by giant planet migration, mostly Neptune. Within this planetesimal belt, there is significant resonant structure. About 20% of the large objects are in mean motion resonances with Neptune. And we know exactly where the planets are. Just think about how excited you would be if we had this kind of precision for an exoplanet system. I mean, a Jupiter and a few Neptunes with a several hundred-year observation baseline, that's pretty good. And we know exactly where the planetesimals are. So unlike in debris disks, where you look at the dust and you infer where the planetesimals might be, here we see the planetesimals and we have to try to guess where the dust is, because although there's many very good dust models, there's no real observations of light from dust in the Kuiper belt. So I'm going to be talking about the Kuiper belt as seen by the Canada-France Ecliptic Plane Survey, which was carried out over a period of about 7 years. So this is the observation blocks on the sky, obviously following the ecliptic, as the name would suggest. Here's the galactic plane. Here's another view looking down on the solar system. Here's Neptune. Let's see, the observing blocks here, the inner edge is set by a rate cut at 20 AU because we weren't really interested in stuff inside 20 AU. And the outer edge of these blocks is where a 100-kilometer object would be too faint to detect. There's a couple of gaps you'll notice. This is the galactic plane. It's hard to find objects in front of the galactic plane. And this is February on Mauna Kea, when apparently Mauna Kea is overrun by invisible cows and it becomes dangerous to observe. This survey was carried out with CFHT Megacam, which was a beautiful instrument for the survey. It's a square degree field, it doesn't usually look this awful. This was actually from a Jovian moon search, so Jupiter's right up here reflecting all over the place. But this survey wouldn't have been possible without this instrument. So the way this works, just to walk you through how the Kuiper belt objects are detected. So there's an initial discovery block, pick a patch on the sky, and you just wallpaper it with megacam fields. You do this, you look at each field about once an hour, and you do this 3 times, and then you look for objects to move in these triplets. Then you go back to the same field, moved over, because the Earth has moved. So you go back and look a month later, you go back and look another month later, and maybe even another month later. So you have a 4 or 5 month baseline to predict orbits from, and then a year later, you go back and see where go recover the objects. These are actually predictions. There are error bars on this plot. You can see one of them, I think. So this just shows you the power of this 5-month baseline for getting the orbits. And then with a recovery at a year later, and then maybe even another year later, we have really good orbits. So these orbits are, you take the position of the object and you plug it into n-body orbital integration code and run it for 10 million years. So this allows you to diagnose resonances. So this is the resonant angle, which basically shows the position of the object relative to Neptune. So if the object is resonant, this resonant angle will not take on all values between 0 and 360. It'll be confined. So this is an object that's in the 3:2 resonance. If that resonant angle is going through 0 to 360, it's not resonant, and then you can place the object based on its eccentricity and semi-major axis. Then there's also objects that change their semi-major axis or their eccentricity quite violently over the period of 10 million years, and those are objects that are currently interacting with Neptune or some of the other giant planets. So there were about 170 objects that were detected by this survey. And so I'm going to show where they are and just sort of walk you through the structure of the Kuiper belt. So this is 7 major axis versus inclination and eccentricity. Here's Neptune for reference. So this is the main classical belt, which is between the 3-2 and 2-1 mean motion resonances with Neptune. There's a few objects that are just outside. These are the inner and outer classical belt. There are detached objects, which have pretty high eccentricities and are fairly far out, but they're not such high eccentricities that they're interacting with Neptune currently. There's scattering objects, which are currently interacting with Neptune or the other planets. And then there's resonant objects, which have high eccentricities, but because they're in mean motion resonances, are protected from close interactions. So here's another view of these detections, again looking face down on the solar system. So the structure is caused by Neptune's migration outward, and there's a few theoretical models for this. There's smooth outward migration models where Neptune's migration is actually driven by scattering planetesimals. And there's the Nice model, which you've probably heard of, where Neptune ends up, there's a huge dynamical instability with the 4 giant planets, and Neptune ends up getting put onto an eccentric orbit, which damps down and it migrates outward a bit. And that sweeps up objects into mean motion resonances. So these two main theories, there's lots of variations. They don't quite match the observations, but there's been several iterations, they're getting better. That's the basic idea. Neptune moved. So I want to walk you through how we actually take these observations and get the true populations and orbital distributions, just to show you the power of this technique. So we start with just a background population of objects, and we look at the cumulative distributions of 5 different parameters: the eccentricity, the distance at detection, the libration amplitude, which has to do with that resonant angle if it's a resonant object, the inclination, and the visible G magnitude. So then here's the background population on the sky. So because we know each of the blocks, we know how deep each of the blocks were, and we know the detection efficiencies in each of those blocks. So we can simulate observing this background population and see what we would have detected from it. So then we get detected distributions. So these are the distributions that are now biased by our survey. And we can compare those with the real detections. And we can do this using statistical tests to actually robustly say how good this model is. And I don't want to bore you with the details. I just want to show you how powerful this is. So we can, so for the Plutinos, there's only 24 detections. These are the objects in the 3-2 mean motion resonance. With only 24 detections, we can very precisely constrain the inclination distribution using, we just use parameterization sin I times the Gaussian. We can constrain the distribution of libration amplitudes. We can constrain the distribution of eccentricities, and that's supposed to be an alpha. It's basically the size distribution of the objects. And so we can constrain all 3 of these using these cumulative distributions and statistical tests and our survey simulator. We also, 2 of these 24 objects are also in the Kozai resonance. If you're interested in this, there's a paper with way too much detail on the Kozai Plutinos here. So we do include this Kozai component. Even with just 2 detections, we have enough. That's enough that we have to include it. So then we do the same debiasing process for each of the components, including the classical belt. And the classical belt is particularly interesting because there has to be these 3 components in order to match the observations. There's a hot component, a stirred component, and a really tight kernel component. So just to show you the results of the debiasing, so here's the same plot we saw before. These are the detected objects. So then here are the true, the relative populations here are correct to within a factor of a few. And so you can see there's a lot of stuff out here that, you know, if we, the biases against detecting these are huge, because as you go out in the solar system, you're looking at reflected light. The flux that you get back drops off as 1 over r to the 4th, right? So there's huge biases against detecting these. So if you see one, there has to be a lot out there. And this is true of the more distant resonances too. So here's the same thing looking face down on the solar system. Here's the detections, and then this is what it actually looks like. This is, and in this plot, you know, these little tiny dots, this is the absolute number of objects, of large objects greater than 100 kilometers. And so you can see it's really dominated by the classical belt. In this plot, the red objects are the resonant objects, so you can kind of see a little bit. Maybe that's significant. So let's look at this a different way. Here is just the number density, just a contour plot of the number density, and you really can't see the resonances at all. You can see this nice ring. Looks kind of familiar from yesterday's talks, right? Kind of like Fomalhaut, maybe. There's this nice ring that's constrained by Neptune. So then looking just to double check this, so here's the same, this is on the same scale. This is the classical objects, these are the resonant objects. And you can see that just because, so there are 20% of the objects are in resonances, right? But because the resonances are more spread out in semi-major axis than the classical objects, the number density is just not there. You just really can't see them. So this is just a real quick and dirty flux model that I threw together. There are many people in this room who could do a better job of this. I'm hoping that maybe there's someone in this room who's already downloaded the CFEPS model and has already done a better job. So this is just using fairly large dust grains that wouldn't migrate very far from their source populations, and just modified black body dust grains. And these two plots are on the same scale. So you can see there's no big surprises here. You can't see the resonant structure at all. You just see this ring, and it's obviously a lot easier to see it edge on than face on. So the Kuiper belt is our very own debris disk. It has been sculpted by giant planet migration, and it contains many objects that are in resonances. But despite the fact that there's so many objects in these resonances, you can't actually see it when you step back. No current giant planet migration models really reproduce the structure perfectly that we see. And the CFEPS model is the debiased model that I show here is the most accurate model of the Kuiper belt for large objects. And this would be a very good starting point if you're doing collisional dust models of the solar system. So just to drive this point home, why should you use CFEPS when there's only 170 objects that were detected, but there's hundreds or thousands of objects in the Minor Planet Center database? Well, the Minor Planet Center database does have all these objects, but it's a whole collection of many different surveys with different limits and different goals and different biases, which are not reported. The objects that are in the Minor Planet Center database are not followed up rigorously, and they're often quickly lost. Many of the objects are initially placed in incorrect orbits and are also quickly lost. And the non-detections aren't reported at all. So in CFEPS, the non-detections were an important part of constraining the model. So debiasing the Minor Planet Center database to get the true populations is impossible. You need a standalone, well-calibrated survey to do that. So with that, I would like to encourage you, if you're going to do this kind of thing, to please download the model from cfeps.net. Thank you.
Thank you very much, Samantha, for a very interesting talk. Bruce, up at the top, please.
It's a very nice. For your toy model of the toy model of the emission from the Kuiper belt, what order of magnitude is the LIR over L star? You know, what fraction of the light from the sun is getting rescattered into?
Oh, let's see. So I didn't do it very carefully.
Okay.
So I don't actually have an absolute number for you.
Okay.
So, like I said, this is really, the point of that was to kind of encourage all of you to do a better job.
To go do it better, yeah. So. It'd be just a very interesting, now that you've got realistic densities, it'd be a very interesting number to see.
Yeah, exactly. Thank you.
Okay. Next question there, please.
Hi, Samantha. Excellent talk. I'm just wondering, what is the total mass in Earth masses of your device, Kuiper belt?
Oh, okay, well, let's see. There are, so we get that there's, what is it, 130,000 objects greater than 100 kilometers in diameter. So what does that add up to? Try to do order of magnitude on my feet. I don't think I can do that quickly in front of lots of people, sorry.
Okay, next question, just there.
I would expect some Neptune Trojans, because you could find them.
So CFEPS, we had expected to find some, and we didn't. The paper, we actually went back and did an upper limit, and used other people's observations, and we got that there should be less than 300 to 400 Trojans. Greater than 100 kilometers, so it wasn't unreasonable that we didn't find any.
Okay, thanks.
Yes, one question down here.
Hi. Would you detect a retrograde component, so counterclockwise orbits?
Oh yeah, because I mean because we actually go and look at the N-body simulations, we would have found one like that. There were, not in CFEPS, there were a couple of related surveys where we did find weird angles. I mean, we were just looking in the ecliptic plane, so those ones are really hard to detect. But there's a couple of other surveys where we followed the same routines looking off the ecliptic, and we did find some, so.
Okay, and the final question, just up there, please.
Do you have color information on your detected objects?
Sorry, what?
Color information.
Color, not very good color information, so.
How many colors do you have?
Just 2.
Okay.
And yeah, the error bars are pretty big on some of them, so it's not great. But that's in the Petit et al. Paper if you want to look at that.
Okay, thanks.
Well, let's thank Samantha again.